Hi, this lesson is about differentials and linear approximation. So both of these have to do with the derivative. And if you recall, the derivative definition came from what we understand about the slope of a line. The computation for the slope of a line is based on 2 points that we call x sub 1, y sub 1, and x sub 2, y sub 2. And your change in y over change in x gives you your slope calculation. That's a measurement of the inclination of the line. And then as the 2 points get closer and closer together, the difference between your x values approach 0, and that brings us to the derivative. And we use this notation to represent the slope of a line, but you're taking that limit as h approaches 0. And then we learned rules to avoid using this definition. Sometimes that definition could be a little cumbersome to work with. So we have rules that are shortcuts to give us the answer for the derivative. But remember that the notation for the derivative can also be written like this, dy over dx, which looks somewhat like our original slope formula. And when you think of it in terms of dy over dx, we're going to consider it as a ratio, an expression of a numerator and a denominator. And that numerator and denominator, dy and dx, are called differentials. And differentials have meaning. So first, a differential is computed the same way you compute derivatives, except instead of writing dy dx on the left side, your dy will be on the left and the dx will be on the right along with your derivative. So for this first example, if I wanted to know what the differential dy is for y equal to cosine of 3x, I have to use chain rule on cosine of 3x. And so when you do that, the derivative of cosine is negative sine of 3x times the derivative of 3x, which is 3. So my derivative is negative 3 sine of 3x. But instead of writing dy dx, you write dy equals negative 3 sine of dx, negative sine of 3x followed by dx. Another example is here on the right in red. If we wanted to find the differential dy for y equal to x squared sine of x, you're essentially taking the derivative of this side, but you're writing dy on the left and dx on the right. But all of this in here is the derivative, and here we use product rule. So remember, product rule is your first function f times the derivative of the second one. Derivative of sine is cosine, and then it's the derivative of the first one, which is 2x, times the second function, which is sine. So we put that in parentheses because the dx is being multiplied by that expression. Okay, so why do we use differentials? So you could use differentials in order to estimate the value of delta y at some values, whatever values x are. So remember, with delta y, you're just subtracting two y values. And so your differential dy is approximately equal to your delta y. And your and your dy, just as I did in these previous two examples, is basically the derivative of your function at some value followed by the differential. So if you recall your point slope formula, this formula that I just showed you right here is related to that because delta y is the difference in values, y minus y sub 1. And then f prime, well, we know that the derivative represents the slope, so that's the m part. And dx, well, that's your differential for x when your x's are really close together, so that's x minus x sub 1. So the concept of differentials as well as linearization that we'll talk about soon is related or very closely similar to your point slope formula, which is used to find the equation of a line. So suppose I wanted to compute delta y and dy for this function y equals e to the x when x is equal to 0 and delta x is equal to 0.4. So delta y is just the difference in two y values for these x values. Now I have to figure out what those x values are. So if delta x is 0.4, then that means that your first coordinate is 0, which was given, and the second x value must be 0.4 because the difference in them, delta x, x sub 2 minus x sub 1, must equal 0.4. So I have to plug in 0.4 in for x minus 0 in for x. And so e to the 0.4 minus e to the 0, you would need a calculator to compute that because e to the 0.4 is an irrational number. And we end up with, it's about 0.492. Now we'll compare it to dy, and it should be close. To compute dy, I basically take the derivative of e to the x, which is itself, followed by dx. Now, we know that the original value is at 0, so you plug in 0 for x, and my delta x is my dx. When your delta x is small, it is your dx, so I plug in 0.4 for dx. I know that e to the 0 is 1, so 1 times 0.4 means that delta y is equal to 0.4, which is approximately equal to my delta y. The closer your x values are, the better your approximation is. So if instead of 0.4 I had 0.1 or 0.01, this number and this number would be even closer together. Here's another one. We want to estimate dy for y equal to the natural log of t squared for t sub 1 equal to 1 and t sub 2 equal to 1.01, and then compare it with the calculation for delta y. So let's do our dy first. So we take our differential. For this function, I have to use chain rule. So it's 1 over t squared times 2t followed by dt. When you simplify it, you get that your differential dy is 2 over t dt. Now my original t value is 1, so that's what I'm going to plug in. And my delta t, which is about dt, is the difference between these two t values, which is a value of 0.01. So we plug in 0.01 for dt, and we plug in 1 for t, which is exactly what you see here. So we just make our substitutions there. And that tells me that dy is 0.02. And remember, dy is an approximation of delta y. So now let's compare that to delta y. So I have to plug in my t value. So I take the natural log of 1.01 t squared minus the natural log of 1 squared. Well, the natural log of 1 is 0, so we need to plug this part into a calculator, natural log of 1.01 squared, and that tells you that delta y is about 0.199007. And you can see that dy is a pretty good approximation of what delta y would be. Okay. So we can also use differentials to estimate the value of a function by a process called the linearization of a function. It is also called linear approximation. So linear approximation means that we're going to estimate the value of f of x at some value a when your delta x is small. And when delta x is small, we say that's equal to dx. And linearization is a specific formula. So your function f of x will be approximately equal to the linearization, that's why we're using L here, L of x, which is equal to f of a plus f prime of a times x minus a. So although this might look like a new formula to you, it's actually another formula that is closely related to the point-slope formula. So recall that the point-slope formula looks like this. Y minus y sub 1 equals m times x minus x sub 1. If I solve this equation for y, then y sub 1 ends up on the right. So I have y sub 1 plus m times x minus x sub 1. That represents the equation of the line through the point x sub 1, y sub 1 with a slope of m. The linearization formula, which is the one in the box, looks like this. L of x equals f of a plus f prime of a times x minus a. And we know that represents the linearization equation through some point, and this time my point is called a, f of a, so here's your a, and here's your f of a, with a slope of f prime. So if you look at the line above, f of a is my y value, f prime is my slope, and x minus x sub 1 is just x minus a, so my x value is a. So they are actually the same equation, we're just using different notation. So since the tangent line to a curve at some point AF of a is very close to the curve, at some value x that's close to a, then we can approximate the values on the curve by using the values on the tangent line. So the purpose of linearization is to get the value of a function when the function would otherwise be quite difficult to compute, but lines are easy to compute a value. So these were especially useful before computers and calculators, so it gave mathematicians and scientists ways to compute values that would otherwise be very difficult to compute. So first let's practice using the formula. We want to determine the linearization equation of y equal to 4x cubed minus 2x at a equal to 1. All right, so remember my formula is the one right here. So I need f of 1, I need f prime of 1. And so f of 1 means you just plug in 1 right in here. So that tells me that it's 2. And to find f prime, I have to take the derivative, so that'll be 12x squared minus 2. So I plug in 1 into that, and that gives me f prime is 10. So now I can plug it into this formula. So I get L of x is equal to 2, remember this is f of 1, plus my derivative, which is f prime, and that's equal to 10, times x minus 1. And when you take that equation and distribute the 10 and combine like terms, you get that your linearization is equal to 10x minus 8. Okay, so in this next example, I'm going to show you why this would be convenient in order to help us compute values. So we want to find the linearization of the function f of x equal to the square root of x plus 3 at a equal to 1. So by the way, a doesn't always have to be 1. It's just a coincidence in these two examples. At a equal to 1, and use it to estimate the value of square root of 3.98 and the square root of 4.05. And then we will determine if our estimations or approximations are an overestimate or underestimate. Okay, so to find the linearization, I again need to compute f of a and f prime of a. Now, f of 1 for this problem is 1 plus 3. Square root of 1 plus 3, we know that's 4. And so my function value is 2. Again, that's just a coincidence that these work out the same way. That's not always true. F prime of x, remember this is x plus 3 to the 1/2, is 1/2 x plus 3 to the negative 1/2. So when I plug in 1, you'll get 1 over 2 square root of 1 plus 3, and so my derivative is 1/4. So now that I know that the derivative is 1/4 and I know my function value, I'll show you where my answer comes from. I have L of x is f of a, which is now 2, plus f prime, which is 1/4, times x minus 1. So that is equal to 2 plus 1/4 x minus a fourth, but 2 minus a fourth gives me L of x is equal to 7/4 plus 1/4 x, which is exactly what I said here. So that's our linearization. So if I wanted to evaluate what is the square root of 3.98 by using my line function, that means I have to rewrite the 3.98 in terms of my original function. Remember, it's originally x plus 3. So therefore, my x value has to be 0.98. 0.98 plus 3 is 3.98. And now we know that that value is approximately equal to my line. So I plug in 0.98 into my variable. So I get 7/4 plus 0.98 divided by 4. So this ends up just being the addition of two decimals. You can convert this to a decimal and this to a decimal when you divide. And that gives me an approximate value of 1.995. If I do the same thing to approximate 4.05, that means that my x must be 1.05 because 1.05 plus 3 is 4.05. So if I plug in 1.05 into my line, my linearization, and compute that, you get that the approximate value of square root of 4.05 is 2.0125. So now we have two approximations, these two right here, and we're going to compare it. If I were to plug this into a calculator, the square root of 3.98 is 1.9949937, and that goes on and on because this is irrational. Notice that this was my approximation. Pretty good. It's slightly higher, so this would be my approximation is an overestimate of the true value. And my calculator gives me this number for 4.05. And remember, this was the approximate value, 2.0125. So again, the line gives me a slight overestimate, but nevertheless a very close value. So again, before there were computers and calculators and things like that, if a mathematician or scientist wanted to compute the square root of 3.98, the linearization gave them a pretty close estimate of what that would be. Because this could definitely be done by hand. This, no, cannot be done by hand. At least not in a reasonable way. So let me explain why they are overestimates by showing you the graph. So the graph of the square root of x plus 3 is in red. And so it's this curve, and my line, L of x, is in blue. So you can see at a equal to 1, which is right here, I have that point where the tangent line intersects it. And so the line is slightly above the curve, but when I'm close to that value, like here when I plugged in 0.98, that's close to 1. That's why I got a value that was close to the actual value. And when I plugged in 1.05, that's also close to 1. And so we got very close approximations. So that's it for that lesson. Give the homework a try. Good luck.